recording. All right. Welcome. So this week is a little bit different, right? Because Thursday is the day for truth and reconciliation. So there's no classes, right? And so no classes on Thursday. And then we, of course, have a lab scheduled. But what I decided to do was give you guys a little bit of maybe free time. So what you can do for the Friday lab section, we're not going to meet together. I'll get you to watch the video for it that I've posted already. And then there's some exercises at the end that you can do. And then you'll have to hand that in and you have a week to work on that. Okay, so today is the only time that we'll meet in person this week. And then we'll see each other on Tuesday next week. So that feels weird, but hopefully that gives you a little bit of downtime and just kind of figure things out, because things do get a little bit busy this time in the term, right? So for this week, for Thursday, there are no classes. Okay, and that goes for all your classes. For the Friday lab, we are not meeting in person. Just watch. And this is where it got complicated because I called the birthday problem lab 2, but then this is lab 2 from that lab manual that I posted. And so got a little bit confusing, but just watch the lab 2, which is now lab 3 video. Okay, so I want to show you where I put that, but it's pretty obvious, but just so you can see, if I go to, is this our Moodle page? Yeah. So if you're not sure where the lab stuff is that I'm referring to, it's the lab notes for the YouTube videos. There's a PDF posted. And so we're going to go through the lab 2 there, which is really just getting you sorted with pulling in different types of data sets. And there are lots of different ways to do it. So here, this is today or this week, I guess. Week 4 already, crazy. So here, watch the lab 2, which is now lab 3. That's confusing video. And so I just wanted to show you what I meant by that. And that's going to be here. So I put the link here. Lab 2, which is now lab 3 recording. Okay. And if you want to, you could just read the instructions in the lab 2 section of the lab manual that I've posted at the top of the Moodle page. Okay. And so here, right, today we're going to continue chapter 1. I couldn't remember which section it was, so I just wrote chapter 1. I'll fix that. It's 1.3. And then 1.3 is huge. Thursday, there's no classes, okay? And then for Friday, watch the lab 2 recording on your own and complete the lab assignment on your own, right? So we were not meeting in person. I posted, I called it the lab 3 template. I got to figure out the naming strategy here because it's getting very confusing. But anyways, there's the template that I refer to in the exercises. So you can just grab that and save it as an RMD file, and then your Dropbox for the exercises. Now for this one, this is new for us, and this is just to get us up to speed. And maybe you already have some sort of LaTeX or tech distribution installed, and that's great. Then you're able to knit to PDF. But what's new for this one, for this lab, is that you're going to have to install And the reason I'm being vague about it is because it depends on if you're on a Mac or on a PC, or maybe what's that, Linux or whatever. Anyways, I don't know. So it depends on what type of computer you are. You will have to Google your way to it, right? How can I install this on my computer? And how you're going to check to make sure that it's running is you're going to knit to PDF, and then it should produce a PDF document. Okay, and so there might be some troubleshooting on your end, right? Making sure that it's up and running, but that's part of this lab. Okay, and so this is part of the exercise of the lab, right? Figure out how to install LaTeX, okay, or tech. There's Tech Shop, there's MikTech, there's Tiny Tech. I'm not sure if that would have everything that we need, but probably. So there are lots of different tech distributions that you can choose from. So figure out how to install LaTeX and be able to knit to PDF. And be able to knit to PDF. Now it's possible that you already know how to do that, and that's great, right? So then it's all easy. But if not, it's going to require a little bit of work and just kind of Googling and finding your way to it. Okay, good. So here I do want to highlight that we are not meeting in person on Friday, right? So that time is yours. Whenever you want to work through the lab, that's up to you, right? And you don't need to watch the video. You could just read the instructions. It's just a lot of people seem to prefer to watch me read the instructions to you. I don't know, maybe not. So that's kind of the update for this week. Okay. I feel like I had another thing I wanted to mention before I kept going. Yeah, so if you prefer watching video, that's why I made them, because a lot of people prefer it instead of reading. They're the same. So don't worry, you're not missing anything if you want to just read the instructions, or if you want to just watch the video, that's fine too. Yeah, way more interesting. Okay, so I think that was all I wanted to do. So try getting set up, trying to knit to PDF, see how it goes. Okay. And you have a week to work on it, right? So I made it due, I think, October 8th. So that's next Friday. Okay, so you've got lots of time to get in touch with me and ask me questions if it's not working. Okay, so for some quick review, because there's a lot of information in this section. And so we were talking about counting rules, and I managed to just squeeze in permutations last Friday, right? I didn't quite finish it in class, and so I said, oh, I'll just finish it in the lab. And then I posted, so my voice has been doing something weird. So I'm trying to not talk so much, which is really hard because my job is talking. So, so I'm trying, if I have a video that I can use, then I'm trying to do that. But I find that my voice is like a muscle. So at the beginning of the term, it needs to kind of work itself up, and then I get stronger and stronger. I can talk forever. So we talked about counting rules. The first one, we're going to talk about 3 different counting rules. The first one was the multiplication rule. or the MN rule or M by N rule, which really just says that if you have a set with M elements and a set with N elements, then there are M times N possible outcomes. Okay. In a set with M elements, combined with a set of N elements, there are MN, so M times N, possible ordered pairs. Okay. The second counting rule that we talked about and finished talking about, and even had that birthday example in the lab last week, right? Just as an example of permutations. Well, is permutations. There, I gave it away. So the second one is permutations. Permutations are going to be the number of unique, I don't want to say permutations, but the number of unique sets with K elements. Okay. So that's it for our review. So I'll put a little end here because I've got a page break here, so I'll keep it on the same page. But then the new one and the last one, the last counting rule that we want to talk about is combinations. Okay, so combinations are different from permutations because now we want to talk about how many possible subsets of size K can I make from a group of N. So now the order doesn't matter. It's just how many possible ways could I make this happen. Okay. And so combinations are the number of subsets of K elements taken from A with N elements, right? That's kind of the what we've assumed this whole time is that A has N elements. So the number of subsets of K elements taken from A with N elements, notice, right? These are not unique, right? These are just how many subsets can I make, right? Not unique. Whereas here, permutations was the number of unique sets with K elements, right? And so now I'm counting the number of subsets of K elements, okay? And so what I like to do is I like to illustrate the differences with just a quick tree diagram, okay? And so we're not gonna do the calculations, but I'm gonna show you what the differences are. Okay, especially for combinations. Okay, so combinations happen when we have things like a tree diagram. And just so to keep our tree kind of reasonable, let's say we're flipping a coin, right? And then, but let's say that the coin kind of changes probability maybe. Okay. And so, for example, consider flipping a coin three times. Otherwise, the tree gets huge. So in my first flip, I either get heads or tails. Then in my second flip, so here I'll just highlight, flip number 1 is on this first level. And then I'm going to have flip number 2. And I'm going to try to keep it on just these 3 lines. Usually that's hard, so we'll see how I manage. But flip number 3 is going to be in the second level, or third level rather. Flip number 2 has 4 possible outcomes because it could be head, 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 tail, tail, head, or tail, tail. Okay. Flip number 3, so now each of these 4 has 2 possible outcomes. So you can see how if I went for 4 flips, this tree kind of balloons out very quickly, right? And so here, it starts to look like this. Head, tail, head, tail, head, tail, head, tail. So now, when we're talking about combinations, combinations are just looking at, for example, how many ways could I have 2 heads and 1 tail? Okay. So a combination in this case would be how many ways could we have 2 heads and 1 tail? Okay. So now these are not distinct anymore. These are unique. So what I like to do is I like to start here at the head. So I have 1 head, and then if I go to a second head, then my next one has to be tails. So what I do is I show that outcome like this. And then I do the same thing. If I start here at the head, as long as I have 2 heads and 1 tail, then I can go head. And then I've already done that branch. So then if I go down the tail branch, then my next one has to be head. So then I can go like this. If I start with a tail and then I go for a head, my next one also has to be heads in order to satisfy that 2 heads and 1 tail criteria. So then I go boop, boop, boop. If I start with a tail and I go down the tail branch, there are no options where I could get 2 heads and 1 tail anymore, right? And so we see that there are 3 possible outcomes. There are 3 possible subsets with 2 heads and 1 tail. We see there are 3 possible outcomes. Yeah, there are 3 possible outcomes with head, or I shouldn't do the order here, with 2 heads and 1 tail. Okay. So that's when we need to use these combinations. So let's see here. In combinations, order is not important, right? We said it could be heads, heads, tails, head, tail, heads, right? Order is not important. So in combinations, order is not important. Yeah. And we are counting the number of subsets the number of subsets of K elements taken from A, which we know has n elements. Okay, so if we go back to our permutations and think about unique subsets, right, then we can say that by the permutation rule, it generates P K. So choosing K elements or K unique elements in a set of K, which is, or from a set of K, which is K times K minus 1, all the way down to 1, which is K factorial permutations. Okay. Or really, just to clarify, unique permutations of K elements. So now, what if we dip back in and we select another subset size K, and it's also unique, right? So now we can keep dipping in and keep getting all these different unique permutations, right? And so if order is important, heads, heads, tails is unique from heads, tail, heads, right? Which is also unique from tail, head, head. Okay, and so these would be unique permutations. Okay. And so if we select another set of K elements, we would find there are PKK distinct permutations of those K elements as well. Okay, so that's kind of like, ugh, what a mess. But that's what it is, right? And so, all right. We would find that there are another PKK distinct elements or distinct permutations of those K elements as well. Okay. So this is all leading towards combinations, which is when we don't actually care about the distinct permutations, right? We just want to know how many possible subsets can I have of size K. And so each permutation of K distinct elements drawn from A must be generated by one of those subsets, must be generated by one of those subsets. Okay. So what we get is that one of those subsets comes from a collection, and that's the combinations, which we denote by n choose K. And I'm going to introduce it in a formula so that we can derive it from this formula, which I know feels a little bit weird, but I'm going to talk about it. So therefore, PKK permutations is actually going to be n choose k, and I'll clean that k up, times k factorial. Okay, so here, this is n choose k, which is the number of possible subsets. And then k factorial, that's how many unique permutations there are, right? And so what we get is we can solve for this n choose k. Okay, so notice how there's no fraction in here. It's just n choose k. I'm assuming that you've seen this at some point, and so it shouldn't be foreign. But what we can do is we can divide both sides by k factorial, right? And so n choose k is going to be pkk divided by k factorial. But remember, pkk is actually pkk is n factorial over n minus k factorial. So what we can do is we can rewrite this as n factorial over n minus k factorial times k factorial. Okay, and so this formula is how you calculate n choose k. And n choose k is the number of possible subsets of size k. So we say that there are n choose k, right? So here, read it as n choose k. Or sometimes on your calculator, if you're using your calculator, or we can say big C K N K. Combinations or subsets, right? But we are talking about combinations, so why not? Of k things taken from a set of n things. Taken from a set of n things. Okay. In terms of the example, usually what we would do is, so in terms of this tree diagram here, I've flipped a coin 3 times, right? Flip 1, flip 2, flip 3. What we could do, because there are only 2 possible outcomes, then what I can do is I can talk about 2 heads, right? So now I would have 3 choose 2, which happens to be the same as 3 choose 1 tail. Okay, and so here can go back to in the tree diagram. Oops. We considered how many ways we could have 2 heads. We considered how many ways we could have 2 heads, right? Which implies 1 tail. In 3 flips. So what we saw was 3 choose 2. So what we saw was 3, choose 2. Two heads in this case. There are the same number of ways to have choose 2 tails, right? It actually doesn't matter. In fact, it becomes the same value if we look at 3, choose 1, right? Because 1 tail, or vice versa, 3, choose 1 heads, right? And so 3 is kind of a boring number because there's not a lot going on. And so for more interesting things and kind of more breadth in the number of subsets that you can create, you'd have to go for more than 3. But this one is easier to visualize. I just realized I'm going to show you guys, just in case, 3, choose 2 on your calculator. And I've got a calculator here. It's not, it's not the best one, but let's do this one. Oh, I forgot. It always has ads. But so see over the plus sign, there's the NCR. So if I do 3 second NCR, it doesn't do anything because it's a weird calculator. Choose 2 equals, and then I get 3, which matches up because we found that there were 3 different ways of doing it, right? So, but now if you wanted to, you could build a tree with 4 flips, right? And how many ways could I get 2 heads and 2 tails, right? We're just focusing on 2. So now 4, choose 2. There are 6 different ways that you could do that. So you can confirm that with your tree diagram, just trace out all the different options, but it quickly gets out of hand. Okay. So what we found was that 3, choose, oh, sorry, I did a fraction for some reason. 3, choose 2 is 3, right? 3 different paths. Okay. Now, there are some additional properties of probability that I'm going to parking lot for a little bit. There is one in particular that I want to discuss, and we've seen it. It's just an extension of something that we've seen already. And so I always like those examples. So 1.3.2, I'm kind of cutting it short here, but we're going to get the gist of it. So additional properties of probability. And I'm going to say recall, but I'm also going to give you the theorem. So recall theorem 1.3.5, which says if A and B are events in the sample space C, and this should look familiar, then the probability of A or B is going to be the probability of A plus the probability of B minus the probability of A and B. We've seen that before. In fact, we proved it, right? And so this is what we call the general addition rule, or the general additive law. The general addition rule / general additive law. That sounds a little scarier, but it means the same thing, general and additive law. I call it the general addition rule, doesn't matter. Okay, what's cool about this, remember in terms of our Venn diagrams, right? I've got A circle, B circle, or maybe a B circle like this, right? What we have to do if we want to know the probability of being in either A or B or both, we have to subtract that overlap once, right? And so that's what that general addition rule does. So that we're very familiar with, hopefully. And we can extend this law. We can extend it to more than 2 sets. In fact, we can extend it to an infinite number of sets. But for now, let's just talk about, we're going to talk about 3 sets, start there, and then develop the larger one. So we can extend this law, to an additive law for an arbitrary union. Okay, meaning any number of sets. Not just A and B, right? More than 2 sets. More than 2 sets. Okay. So what we're going to be developing is called the inclusion-exclusion formula. And we're going to start by looking at just 3 sets, and then I'll introduce you to, well, this works for any union. Okay, so first, well, I guess first I want to name it here. So it's called the inclusion-exclusion formula. So what I want you to do is first consider this fact. So I'm going to give it to you, and then we're going to talk about it and kind of make sense of it. And we're not going to prove it. You could work through and prove it, and I might make you do it. We'll see how cruel I feel. No, but it's a good exercise. First, consider this. So if I have 3 sets, right? 3 sets is more than 2 sets, just a little bit more, right? And so now I'm going to call it C1 or C2 or C3. This probability is going to be the probability 1 minus probability 2 plus probability 3. Now we need to know what P1, P2, and P3 are. Notice that those are lowercase. And so I'm going to say where P1 is the probability of C1 plus the probability of C2 plus the probability of C3. That's P1. So that's this placeholder here is actually a placeholder for all these probabilities. P2 is the probability of C1 and C2 plus the probability of C1 and C3 plus the probability of C2 and C3. What's going on here? These are all the different ways that I could make subsets of 2, right? C1 and C2, C1 and C3, or C2 and C3, right? But if we have to look at P3, any guesses? You don't have to. I'm going to give it to you right now, but it's going to be the probability of C1 and C2 and C3. We see some sort of pattern here, right? Here I have the individual sets, right? C1, C2, and C3 are all their own probabilities, right? this is a subset of 1. Here I've got a subset of size 2, and here I have a subset of size 3 from 3 possible sets, C1, C2, C3, right? And so what happens is, and we can convince ourselves that this formula makes sense, right? Because, and you can see why you wouldn't want to write this whole thing out. It's easier to just communicate P1 minus P2 plus P3. So P1 is each individual probability. And then what are we doing? Then we're subtracting each of the individual overlaps. But then we have to add on one overlap. So let's just have a look at the Venn diagram just to see why that is. And once you make the Venn diagram, it'll be pretty clear why we have to add it back in, right? Or you could think of the probability of C1 as all of the C1 circle, probability of C2 is all of the C2 circle, then C3 is on the bottom. Now, if I'm looking at 3 sets, a typical Venn diagram is going to look like this, right? Because we want to allow for overlap with each of the sets. Okay. So this is going to be C1, this is going to be C2, and this is going to be C3. Okay. So if I look at C1, C2, and C3, right, then I've got all this overlap here, right? And so then what it says is individually, you're going to go through and you're going to remove this chunk, right? The C1 and C2 chunk. So that's going to be this part, right? Because that's the overlap between C1 and C2. Then I'm going to remove the overlap between C1 and C3. C1 and C3 have overlap here. So that's going to be this overlap. Okay. Then I'm going to pick a different color because that one's not going to work. How about purple? Right. Then I have the overlap of C2 and C3. So now I'm going to cut that out as well. Okay. Which means that if I'm looking at this entire setup, that's going to be everything. If I can draw that out kind of properly here, if I can draw it out like that, right? But notice that C1, well, there's overlap with C2 and C3, so we've taken that out, right? And so now what I'm stuck with is I've got one layer between C1 and C2 in this green area, so that's good. And then I had another layer taken out between C1 and C2, so that's good. And then what happened between C2 and C3, I have another layer removed, so that's good. But there were only 3 layers now. It's going to be hard for me to do three layers, right? 1 layer, 2 layers, 3 layers. Okay, so in the center there, I've actually removed all 3 layers, which means I have to add it back in. So this has to be added back in, and that's going to be this overlapping area. And then I get kind of a smooth surface is how I think of it, right? Just 1 layer all across. And that's what we saw here, right? So we have each individual one, and then we subtract all the subsets of 2, and then we add in the subset of 3 to make sure that there's that there isn't just an empty hole in the middle. Okay. Okay, so how does this extend to more than 3 sets? Okay, so this can be generalized. this can be generalized to the inclusion exclusion formula, which is what we were kind of building towards. Generalized to the inclusion exclusion formula. Okay. Which says that the probability of C1 or C2 or C3 or up to the union with CK, right, allowing for K different subsets or K different sets, and I didn't give myself enough room here. Is going to be P1 minus P2 plus P3 minus the next plus. One tricky way to get that plus minus situation is, okay, so when K is 2, I need a minus, right? And when K is 3, I need a plus. And this is not something that I'm expecting, but it's something I expect you to be able to read. And so what we do is we have -1 to the power of K minus 1, or sorry, K plus 1. I guess -1 would work as well, but cleaner with +1. And I didn't give myself quite enough room there. PK. Okay. So here, right, if I want to talk about maybe this, I'm going to amplify this down here, right, to get, oops, to get the alternating plus minus, right, where we want negatives on the even ones, it looks like when K is even, right? So positive for P1, that's an odd K1. Negative for when K is even. So to get the alternating plus minus and minus when K is even, we use -1, oops, to the power of K plus 1. Okay, because notice that if K is odd, right, then I get an even power, and even powers of -1 are going to be positive, right, +1. So notice when K is even, K plus 1 is odd. So -1 to the K plus 1 is also odd, or is -1. While if K is odd, K plus 1 is even. So -1 to the K plus 1 is 1. And maybe I'll just say +1, positive. Okay, just to clarify what's going on there. So now we have these P1, P2, P3, blah, 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 right? And so now let's define these P's, where Pi equals the sum of probabilities, the sum of the probabilities of all possible intersections, of all possible intersections involving I sets. Okay. So as a quick example, right? For example, and this is going to get pretty big, right? But what if I let I be, or maybe what I'll do is I'll let K be 5. Uh-oh, it's going to get huge. Maybe I don't want to do that. You can play around with it, but how about we don't do that? I regretted it immediately. I guess I could. What's the problem? P2 is fine, except there's a lot of different options. Let's just do P4, K equals 4. That's a happy medium. Develop the inclusion exclusion formula. Develop the inclusion exclusion formula for K equals 4. Okay. Which means that it's going to be the probability of C1 or C2 or C3 or C4 is P1, minus P2 plus P3 minus P4, right? Okay. All right, where P1 is easy because that's the subsets, all the possible subsets of size 1, right? And so C1 is one possible subset, C2 is another possible subset, C3 is another possible subset, and C4 is another possible subset. Right, and so here I'm going to bump this over because I suspect I'll need a little bit more room, but P1 is the probability of C1 plus the probability of C2 plus the probability of C3 plus the probability of C4. That's a lot of writing, of course, but it's not hard. Next up is a little bit harder, right? A lot more thinking because now we want subsets of size 2. P2 is the probability of, and I'm just going to work through them methodically, right? And so an order doesn't matter in this case, okay? And so it's going to be C1 and C2, right? Because it's the intersection of all possible intersections involving I sets, okay? So it's going to be C1 and C2 plus the probability of C1 and C3 plus the probability of C1 and C4. That's C1 out of the way, right? That's C1 attached to each of the other 3 elements. In terms of writing our math, we typically stack our equal signs, and then we like to bump in our pluses a little bit on the next line if we have to overflow, just to show that it kind of links up. So often it'll kind of span this way to show that the calculation keeps going. So now if I move to C2, right? Looking at C2, well, I already have it intersecting with C1, so I don't need that, but I do need to consider C2 and C3. So that's the probability of C2 and C3, and the probability of C2 and C4. Okay. Try to make sure I don't forget any here. So that's C2 joined up. I have all the possible unions with C2. So now I move on to C3. C3, I already have the intersection of C1 and C3, right? And I also have the intersection between C3 and C2. So then I need to consider C3 and C4. I'll add it here. Oops. And C4. And now, right, the only one left is C4, but if I look here, then I have C4 and C3, I have C4 and C2, I have C4 and C1. So it looks like I have all those possible intersections, right? So these are all the possible intersections with two elements. P3, and you can see why I was all gung-ho and I was going to do 5, but doing 5 elements, right? So going up to C5, it's going to get huge, right? Especially once we do P3. So P3, now I'm looking at intersections of 3 sets. Okay, and so what I'm going to do is I'm going to look at these guys for reference. It doesn't matter how you do it, but what I'm going to do is I'm going to look at C1 and C2, and the only one that's missing here is C3. C1 and C2, only one that's missing here is C4, right? And then C1 and C3, I already have with C2. C1 and C3, I can look at with C4, right? Maybe there's a better way to do it. There's a lot of different combinations here. Okay, let's see here. Probability of C1 and C2 and C3 plus the probability of C1 and C2 and C4. That's the C1 and C2 combination. Now, what if I consider C1 and C3? C1 and C3, because I already have C2 here, I need to look at C4. Okay. 1, 2, 3, 1, 2, 4, 1, 3, 4, 2, 3, 4. So now I'm going to look at C2, because I've exhausted all my options involving C1, right? It could be C1 and C2 and C3, or C1 and C2 and C4, I got those, or it could be C1 and C3 and C4, but those are all my C1 options. So now I move on to C2. C2 and C3 and C4 are my only options because I've already done all the ones. C2 and C3 and C4. Then there are how many options? I've done my C1s, and then my C2 options I've done. And then C3, I've got C3 with 1 and 2 and 1 and 4 and 2 and 4. Looks like I've got them all. Okay. I don't think I'm missing one, but it's also getting a little bit, it's a lot. How about P4? Subsets of 4. Well, with only 4 possible outcomes, that's the easiest one, right? Or intersections of 4 subsets here is going to be C1, C1 and C2 and C3 and C4. All right. So P1 and PK are always the easiest ones, and then the ones in between, those are the ones that make you work a little bit. Okay, and so let me just confirm something. 1, 2, 3, 4, 5, 6, and let me just confirm before I go and say something. 1, 2, 3, 4. Okay. For P2, there are 4, choose 2 possible combinations or possible intersections. And for P3, there are 4, choose 3 possible intersections. Right, so you can check it if you want to know how many subsets you should have. The same goes for P1 and P4, but doesn't matter. 4, choose 4. There's only one way to choose 4, and there are 4 different ways to choose 1 from 4, right? So in general, there are K choose I possible intersections. Possible intersections in P subscript I. Okay, that helps if we're having to do these and set these all up and write them out. It helps to know how many we're going for, right? It doesn't tell us what they are, but it tells us how many elements there are. Okay. So going back to letting K be just 2, right? So 2 possible sets. Or maybe I shouldn't do that, but it's kind of a new thing. For K equal to 2, we have this inequality. And so these are just the additional things that that are going to be good to have in our toolbox. And so for K equals 2, we have that 1 is greater than or equal to the probability of C1 or C2. Think about when would it be equal to 1? Well, if C1 or C2 made up the entire sample space, right? So that's the probability of C1 or C2 equals 1 if and only if C1 or C2 is the entire sample space. So IFF is if and only if C1 or C2 are the entire sample space equals C, right? The sample space. Otherwise, in general, the probability of C1 or C2 is going to be less than 1, right? But so this kind of follows from all probabilities being between 0 and 1, right? And they're only 1 if it is the sample space, which means that we can rewrite this, right? So then we have the probability of C1 or C2, which we know now because we saw it before, and also we confirmed it today again, C1 plus the probability of C2 minus the probability of C1 and C2, okay, which we can rework. Okay, so we can rearrange this formula, and I'm going to show you what we're going for here. So which we can rework to find the probability of C1 and C2. So solving for this intersection here is greater than or equal to. So if I'm solving for the probability of C1 and C2, even though I've got this equals and this inequality, what I can do is I can move it over to this side, which means I can also bump it over to this side. And then I can move the 1 over, right? And so what we're going to see is that the probability of C1 and C2 is greater than or equal to the probability of C1 plus the probability of C2 minus 1. Why can I do that? I can only move this probability across the inequality with no repercussions because probabilities by definition have to be between 0 and 1, so they will never be negative, right? So when I add a probability across an inequality, it doesn't change the inequality. Otherwise, that's something that we would have to remember, right? And so here, right, we can rework notice the inequality does not change since the probability of A is between 0 and 1 by definition. Okay, so that's why we can just move it over, because it's always going to be positive, and so then the inequality is never going to change, right? It only changes if we multiply or divide by a negative. And we're not multiplying or dividing here, but it's good to keep in mind that probabilities are always positive. Okay, and so here, this is kind of a weird statement, right? So the probability of the overlap, so the area of the overlap of C1 and C2 is going to be larger than the probability of C1 plus the probability of C2 minus 1. That's just how it goes, right? And so we call this Bonferroni's inequality, but and it's going to come up, but it's only useful for when C1 and C2 are large. Okay, and so we call this Bonferroni's, and it is a really funny name, Bonferroni's. Clean that up. Inequality. Which is only useful, when the probability of C1 and the probability of C2 are large. Okay. So if we mention Bonferroni's inequality, then this is what we mean. But really, just visually, it means that the overlap is going to be larger than the two individual probabilities minus 1, right? The minus 1 changes things, right? Okay, that is all I wanted to do today. And I thought I was going to run out of time, but I guess I talked extra fast today or something. So I'm sorry for that. But I think that's good. So we'll talk about conditional probabilities next week. And until then, I'll let you watch that lab video and work through those exercises and try to knit to a PDF. And then I'll see you next Tuesday. Let me know if you have any questions. Otherwise, I'm going to stop this recording here.